Alright, so here today we're looking at section 12.4, which is all about volumes. All right, so postulate 27 gives us volume of a cube. It says the volume of a cube is the cube of the length of its side, or it said V equals S to the third power, S cubed. Postulate 28, volume congruence postulate, says if two polyhedra are congruent, then they're going to have the same volume. So congruent polyhedrons are going to have the same volume. Postulate 29, the volume addition postulate, just like all of the other addition postulates, says the volume of a solid is the sum of the volumes of all its non-overlapping parts. So all an addition postulate is telling us that a big figure can be made up of smaller figures that we add together, and so we can take the values or the measures of those smaller figures and add them together to equal the bigger figure. And so that works with volumes as well. Take a bunch of small parts, find their volumes, add them together, and have the volume of a larger figure. So the box shown is 2 units long, 6 units wide, and 3 units high. How many unit cubes will fit in the box? All right, so we have 2 units wide. We have 6 and 2 units long, 6 units wide, and 3 units high. How many unit cubes will fit in the box? Well, if we just look at the base layer, we've got 2 times 6, which would be 12. And since it's 3 cubes high, we can take that 12 times 3, say 36 cubes will fit in the box. Or what is the volume of the box? Then we would say 36 units cubed. I don't know what units those cubes are measured in, but whatever units that was is what would be cubed for 36. All right, theorem 12.6, something called Cavalieri's principle. It says if two solids have the same height and the same cross-sectional area at every level, then they have the same volume. All right, so if I look at these 3 figures, they're all different shapes, different forms of prisms. We got an oblique prism, we have a right rectangular prism, we've got a right triangular prism. And it says that the 2 solids have the same height and the same cross-sectional area. So all of 3 of these are the exact same height of the prism. And when we look at the cross-sections, we have a square for the cross-section here. Looks like a parallelogram here. And a triangle here. And if all 3 of those areas are the same, then by Cavalieri's principle, since the cross-sectional areas are the same and they're the same height, they would be the same volume. So for that rectangle there, I said that was a square a second ago, but it's actually a rectangle 3 centimeters by 2 centimeters. So length times width, 3 times 2, 6 centimeters squared. And next one, parallelogram with 3 centimeter and a 2 centimeter height. So that one would also be 3 times 2, or 6 centimeters squared. And the triangle there, it's a right triangle, so we can, that 2 centimeters is the height, 6 centimeters is the base. So we're doing 1/2 of the base times height, 1/2 of 6 times 2, Half of 6 would be 3, and 3 times 2 would be 6 centimeters squared. So all three of these cross sections are the same area, I should say. They're the same height of prism, so we know that those three prisms are going to have the same volume. Likewise, here's some other examples of figures that would follow that principle as well. Now we've got a nice, neat, straight stack of books and kind of a oblique stack of books. But if we look at the books, they're matching books across the way. They're the same height, so the books are going to have the same cross sections. So those two stacks, even though they're not shaped exactly the same, would have the same volume. And even these two stacks of pennies. We have one nice, neat stack that looks like a cylinder, and then we've got a messy stack over here. But all of the pennies are going to have the same cross-sectional area, and they're the same height, or the same number of pennies in each stack. So even though this one's way messier than this one, and this one may look like a bigger volume because it looks more spread out, the actual volume of the two figures would be the same. Alright, so then theorem 12.7, volume of a prism. The volume V of a prism is V equals area of the base times the height. Capital B is area of the base, H is the height. So find the area of a base and multiply it by the height, and we have the volume. Volume of a cylinder, same basic formula, volume equals area of the base times the height. Now since it's a cylinder, we know that the base is a circle, so area of the base will always be pi r squared, and then times the height. So once we know the radius, we can always find the volume of a cylinder with the height. Alright, moving on to some actual examples here now. So find the volume of the right prism and the right cylinder. Alright, so first one here, we have a rectangular prism. I erased it out of here when I was cleaning it up, but those should have a right angle there. Now when we look at this prism, a lot of people will look at the base here, it's 2.5 millimeters by 3 millimeters, and think of that as the base of the prism. But remember, for it to be a base, it has to have a congruent counterpart that's parallel to it. So even though it's not at the bottom and the top, it's at the front and the back, these two triangles are going to be our bases. So those two triangles there will represent the bases, since they're the two congruent figures that are parallel to each other. So to find the volume of this right prism, we're using the formula, volume equals area of the base times the height. And in this case, our base, as we've identified it, is a triangle. So within the triangle, the formula is 1/2 of the base times the height. So with this triangle, we've got a base of 2.5 and a height of 6. So multiply that out. We're going to have 7.5 millimeters squared for our area of the base. And so now to find the volume, we need the area of the base and the height from the prism, which, remember, the height is the distance between the bases. So we're not using 6 here, we're going to use 3 millimeters as our height. So area of the base times the height, 7.5 millimeters squared times 3 millimeters. And then multiply multiply that out, that's going to be 22.5 millimeters cubed. Right? Remember, our volumes are going to have a cubed to the third power. All right, next one is a cylinder. Still area of the base still going to be area of the base times the height, but because it's a cylinder, we get a little more specific formula because the cylinder is always going to have circle bases. So pi r squared times h. So our volume here is going to equal pi times the radius, which is 4 squared, and times the height of 13. So our volume is going to equal pi times 16 times 13. If we multiply 16 times 13, that's going to give us a volume of 208 pi feet cubed, which is in terms of pi. If we go ahead and multiply by the pi, then our answer would be approximately 653.45 feet cubed. So either one of those answers in the homework may ask for it in terms of pi or as a decimal. Alright, so the next one, a little more difficult type of problem. We're going to use the measurements given to solve for x. Alright, so we have a rectangular prism. We're using the formula volume equals area of the base times the height, which in this case, since it's a rectangular prism, the base, or the formula for the base, is going to be length times width. And so we could convert the volume formula for this rectangular prism to length times width times height. So we know the volume, V, is 396, and that's going to equal the length. We have 11, and then the width and the height are currently the same. They're both x. So we go through the process. Multiply 396 is going to equal 11. X times x is x squared. Divide by the 11. It's going to give us 36 equals x squared. X squared on both sides. Alright, x is going to be 6. Or put the units on there, x is going to equal 6 centimeters. Always make sure you put your units when we do anything with measurements. Alright, so then the last one here, we have a right cylinder, volume of 277 feet cubed, the diameter of x feet, and the height of 5 feet. So cylinder, volume equals pi r squared h. So the volume they gave us is 277. That's going to equal pi times the radius, which is actually not x, it's half of x, because they gave us x as the diameter, so radius is half the diameter. So half of x squared, and then times the height, which is 5. So that's going to give us 277 equals pi times 1/2 squared will be 1/4, and the x is squared, which is 5. if I do 1/4 times 5, it's going to give me 1.25. 1.25 pi x squared. And to get the x squared by itself, we can divide by 1.25 pi. And take 277, divide it by 1.25 pi. It's going to give us 70.537. Just taking it to 3 decimal places to give it a little bit of range for the final step here. 70.537 equals our x squared. Take the square root of both sides. And the square root of 70.537 is going to give us approximately 8.40 feet drx. The little squiggly lines there as approximately, because we do, that is a rounded answer. So that completes the notes for volumes of prisms and cylinders.